Here we're looking at a particle size distribution that's been broken down into only 4 channels per decade. And what you can see is that if I were to scroll down the image so we can see the scale on the bottom, that we've got the diameter in nanometers on the bottom and a number on the left called dn/d log dp. So it's a rough estimation of particle counts, but it's actually the particle counts that are going to be in that bin on a log scale. And so we actually have 4 bins. We have a bin right around here that you can't see, that has nothing in it, and then a second bin here, a third bin, and a fourth bin. And those 4 bins are all between 10 microns, 10 nanometers rather, and 100 nanometers. And then we also would have 4 more bins over here between 100 and 200, between 200 and 300, between 300 and 400, and there would be another one over here that would be overlapping larger bins. And so if we go back to the top where I've labeled the center of each bin, you actually see that I'm labeling each bin as 23.7 nanometers, 42.2, 75, 133.4, and that actually gives you the diameters average for each of those bins. What you can see on this slide is the original data that was used to generate that diagram. And so I said we had 4 channels per decade, which means that each channel is a quarter of a unit. So we're working on a log scale, so the log of 10 is 1, and therefore there's nothing in that first bin. The next bin, though, would go from 1.25 to 1.5, and the log of 1.25 is shown over here as the minimum diameter of 17.8, and the log of 1.5 is 31.6. The next bin is going to begin where that minimum diameter left off, in this case 31.6, which is the log of 1.5, and then it goes up to 1.75. So each bin is a quarter unit with the ranges labeled over here, and then the minimum and maximum particle diameters going here. And so what you find here is the average diameter between the logs of those bins, an actual number per cubic centimeter that was recorded for each of those bins, as well as data on diameter, surface, volume, and mass. So these were particles that assumed it was spherical, and so it took the number count and assumed a spherical surface area. So now instead of number per cubic centimeter, it is millimeters per cubic centimeter. And then assumes the volume and the mass as well. And for the mass, obviously, it's just assuming a density and is otherwise a direct correlation from volume. This chart is the statistics, the statistical analysis of that same set of data. And here we see a bunch of different things. We see different measures of centrality, which you read about in the text, including median, mean, geometric mean, mode, and geometric standard deviation. And you see those for the ones that we were most interested in, which is the number counts of particles. And so under here at the very bottom you actually see the total concentration in terms of number per cubic centimeter of particles, as well as the mean diameters, the average diameters for various different measurements of centrality, which you can see some of them are similar. The geometric mean and the median in this case are similar, whereas the actual mean and the mode are significantly different. This distribution was not symmetric, and so we'd expect to see differences. You can then see the statistics as well for the diameter, the surface, the volume, and the mass distributions, including calculations done of the totals in terms of concentration of diameters, surface area, volume, and mass.